All right, we are going to talk about measures of central tendency, meaning we are going to measure where the data are centered. And the reason is we often want one number that describes, possible outcome of an investment decision. And to do this, one thing you might want to know is the average of the data, right? And like I said, we have different types of averages, so it's not going to be as straightforward as you think. But anyway, now the arithmetic mean is by far the most frequently used measure of the middle or center of the data, right? I'll explain what I mean by middle later. For now, let's go with this. So to calculate the arithmetic mean is the sum of the observations divided by the number of observations. Pretty simple, right? We all know that. So if you have like, I don't know, let's say you have few observations, x1, x2, and it goes on, xn. So we sigma, sum it all up, and then divide by the number of observations. So this is how we come up with the average. Everybody knows that. Now, hopefully, if you can recall, I was talking about the population and sample before, and we can compute the arithmetic mean for both populations and samples, known as the population mean and sample mean. This is the formula for the population mean, and this is the formula for the sample mean. And as you can see, they're not different, right? It's the same thing. We're summing all the observations and then dividing by the total number of observations. The same case here. We're just using the big N here and little n here and mu to as the notation to show we are talking about a population mean, and x bar to show that we are talking about sample mean. And like I said, it matters for the reader to know whether you're talking about a population or a sample, right? The average of a population or the average of a sample. Because if you're using the notation mu, and that shows the population mean, that means you have used all the members in that population. And there is no reason to question your result because the population mean is unique. That means given a population, we have only one true mean. But when it comes to the sample, well, it depends on how the sample was collected. So, different samples can result in different means. So when we're talking about a parameter, the descriptive measure for the population, when we're talking about parameter like mu here, no question, we can count on that result. So just a quick example. We will do some proper examples later, but this is just so you know what we're doing here. Now, as an example, let's say you're analyzing all the returns on the companies that are in the pharmaceutical industry in the US, let's say. And you want to look at the average of all the companies' returns and to see how well they have done in, let's say, 2021. We can easily use this formula. That will be, we find out all the returns on the companies, we sum it all up, then divide by the total number of companies in the pharmaceutical industry. And the result, because you have used all the members of the population, it is going to be the true mean of the population, of the returns in the pharmaceutical industry. Now, as for the samples, let's say this is your whole population, all the companies in the pharmaceutical industry. Let's say you wanted to, it was for some reason you couldn't gather all the information, so you wanted to take a sample. Let's say you take a sample from here, so you analyze this one. Let's say you took 30 of them, right? Again, you find out the returns on those 30 companies, you add it all up, and then divide by 30 because your sample is 30, so you divide by the total number. But when you're talking about a sample, like I said before, it's not going to be unique because I took a sample from here, somebody else took a sample from here, let's say. So different samples can result in different averages if you're talking about the average. So just keep that in mind. All right, now means can be computed for individual units or over time. Let's say we have a sample, and our sample is the FTSE Europe 100, which is an index of for the 100 largest companies in Europe, sort of like S&P 500 in US. This is for Europe. Okay, so let's say we are examining the ROE, return on equity, for FTSE Europe 100 in 2013, right? Now, to come up with the mean ROE, arithmetic mean ROE, what do we have to do? We have to find out the ROE for each individual company in the index, right? First company, second company, all the way 100 company. Now, to find the mean, we just have to add it all up and then divide by the total number, in this case 100. Now this data is called cross-sectional data, and the mean that we come up with is called cross-sectional mean. Now cross-sectional data, when we examine the characteristics of some units, in this case the ROE, at a specific point in time, 2013, we are examining cross-sectional data, and the mean that we come up with is the cross-sectional mean. Now to compute the mean over time, let's say I pick one of the companies in the index, this one, and I want to examine the historical ROE for this particular company over time, right? What I'm doing here is called time series data. So I'm examining the historical annual ROE for one of the companies in the index over time. And to come up with the mean is, again, pretty simple. I have my return on equities here. I add them all up and then divide by the total number. That will be 5 years, right? So I come up with the mean. And the mean here is called time series mean. Now here we are finding the time series mean for one section of the index. But it doesn't have to be one section. Whenever you are finding the mean over time, that is called time series mean. So for example, I could do the same thing that I did in 2013 for 2014. That will be finding the return on equity for the first company, second company, 100 company, and come up with a mean. Do the same thing for 2015. Do the same thing for 2016 and 17. Now I have all the means for each individual year, and I can come up with a time series mean here, meaning that I add up all these different means and then divide by the total number. So I have sort of like a mean of the means, if that makes sense. But we will talk about time series data in a later reading. But as for the cross-sectional data, it is very useful when you have cross-sectional data and the mean, cross-sectional mean, because you could use that and then compare each individual company in the index with that mean that we came up with. So whatever number that is, we can compare whether for example, the first company, did they do better than the average or worse than the average? What about the second company? So that would be like a good benchmark to compare each individual company with that mean to see if they have done better or worse. All right, now before we talk about median and mode and sort of continue the measures of central tendency topic, to finish up talking about the arithmetic mean, there is a big misconception about the average, in particular arithmetic mean, that I would like to talk about. Then we will move on to the rest of the measures of central tendency. All right, so let's talk about that misconception that I was referring to before, and we will do that under the properties of the arithmetic mean. So let's say you have done a test. The result comes out and they tell you that you have done better than the average. Good for you. How well do you think you have done? Now, since most people, when we're talking about the average, they think the average is somewhere in the middle. So if you tell them that you have done better than the average, that means they think that 50% of the observations are this side of the average, 50% are on the other side. So you tell them that you have done better than the average, that means they have done better than half of the participants, which is not entirely true. Let me give you a simple example so you will see for yourself. Let's say you have 6 observations. Let's call these returns. Let's say you have 1% return, 2%, 3%, 4%, 5%, and let's say 200%. All right. So when we calculate the average for these 6 observations, what do we get? That'll be 215 We sum it all up, divide by the total number, that will be 6. So we get 35.8, right? Now, as you can see, it's very clear here that out of the 6 observations, 5 of them are less than the mean. Only 1 observation is more than the mean. So clearly that 50-50% split is wrong. Now, where the average leans toward, it really pretty much depends on what kind of numbers you're working with. And, we have these numbers are very close to each other, but we have 200 that is way off. And we call those numbers outliers. And when you have outliers in your observations, well, the mean, the average kind of leans toward that outlier. Now, in this case, we were talking about, percentage and the returns we were talking about, right? If you had, like, let's say the opposite, let's say you have negative, extreme negative returns, then the average would lean toward that negative number if that return is very big, right? So anyway, back to the topic that we were talking about. So clearly, average, when we are talking about average, that's not the center of the observation, right? So what is arithmetic mean? And to answer that, let's say, okay, so this one would be our mean, and these are our observations. Now, the difference that each observation has with its mean, let's call that a deviation, meaning that we have 1 minus 35.8, then the other one would be 2 minus 35.8, and we can do the same thing for each observation. So the difference that each observation has with its mean, we call that a deviation. Now, mathematically, it is always true that the sum of the deviations around the mean equals 0. So that means these are our deviations. So if I were to write it up in a formula, that would be sigma of all the deviations from the mean equals 0. So we add up all the deviations from the mean, we add them all up, we're going to get 0. And that is the arithmetic mean. That is one of the properties of the arithmetic mean. Now, that's not to say that it's not possible that sometimes you have a set of observations and you calculate the mean and the mean happens to be in the middle. It's possible, but it's not going to be the case all the time, right? But yet, unfortunately, a lot of people still believe that when we're talking about the average, they think that, the average, that means half of the data is this side of the average, half of the data is the other side of the average. Unfortunately, still a lot of people believe that. But from this simple example, I hope you understand that that's not the case. So sometimes the arithmetic mean could be misleading. Now, one thing before we leave the screen here, the deviations from the mean, from the arithmetic mean, are important information because they indicate risk. And later, when we want to talk about more complex concepts like variance, skewness, kurtosis, the foundation of all of them is the concept of deviations around the mean. So very important concept. Now, since the average may not be the right approach to find the middle of the data, then what is? Well, it is called median, and we will discuss the median next.